Okay, so we're going to go ahead and get started. These four pieces are things that we're going to be doing throughout all of our calculus work. So specifically with chapter 5, we're going to do some calculus outside of chapter 5 as well. But just making sure you can find the gradient. Again, that's just the slope. So y2 minus y1 over x2 minus x1. So when you do that, what do you get for A? Positive 3/4. So just be careful which way you subtract them. And then when you do part B, we can have fractions in there too. Remembering that dividing by a fraction is the same thing as multiplying by the reciprocal. So for B, what did you guys get? Negative? No decimals and fractions. Negative 12 over 19. Negative 12 over 19. Okay, rational exponents. You guys have seen these before in Algebra 2. This is something that you're going to need to be really confident with, is when you have radicals, being able to write them as fractional exponents. When you have radicals, being able to write them as fractional exponents. So the square root of 7 is the same thing, x to what power? 1/2 power, good. Also, if you have variables in the denominator, you need to be comfortable moving them up to the top of the fraction when possible. So if it's 1 over x squared, I can move that up to the top and make that x to the negative second. Fantastic. Okay, and then the last problem, this is really 8/5. You can kind of do it in 2 steps. But when you have the square root down here, it's like to the 1/2 power, but then I have to move it up. So therefore, it's to the negative 1/2 power, and power to a power we multiply. So that's to the negative 3/2 power. So again, trying to get that so that your x is up top, okay, whether you have a fractional exponent or a negative exponent. Okay, those are things that we're going to do quite a bit of work with here in chapter 5. Problem 3, graphing this. So this is just a rational equation. We call these reciprocal functions in Algebra 2. Thinking about what kinds of transformations they all have. So when you get a problem like this one, do you guys remember having asymptotes in it? So we have asymptotes. Typically our asymptotes were on the x-axis and the y-axis, unless we had some kind of transformations and whatnot that happened. So in this case, what makes my denominator 0? Negative 3, when x equals negative 3. So therefore at negative 3, at x equals negative 3, oh, that's supposed to be a dotted line. And we'll make it a dotted line. There we go. And we'll change its color. Okay, so there is our vertical asymptote, and it also has to have a horizontal asymptote. Good. Well, let's find that color. Where's my horizontal asymptote at? It is at y equals 0. Perfect. Okay, so there are the 2 asymptotes, and we're going to talk a little bit more about why they are where they are in our work today. Question?
I was going to say something about why it's
Okay, and then we need to figure out where a few points are. So back when we were doing reciprocal functions, we plugged in a value on each side of that asymptote to see which sides my graph was on. So therefore, if I put negative 2 into my equation, I get 2 over 1. So at negative 2, it's at 2. So therefore, this is going to look really bad when I draw it. Sorry. Oh, not as bad as I thought. And then I put negative 4 in. So I get 2 over, so negative 4 plus 3 is negative 1. So 2 over negative 1, so that's at negative 2. So at negative 4, it's at negative 2. And we draw that asymptote behavior. Oh, that one's going to look worse. So we're modeling our asymptote behavior for that reciprocal function. But this is something that we're going to kind of see some other similarities with. This we did transformations with, so it had a vertical stretch of 2, and it shifted left 3 units, if you remember that from our reciprocal transformations. And we're just going to build on that a lot more with all different types of rational equations. And then lastly, summation notation. So understanding what we're coming up with here when we're doing sums. So I have to start with 0, so I put 0 in for n, so I get 5 times 1/2 to the 0, which is what? 1/2 to the 0 is 1. 1 times 5 is 5. Woo, okay, let's put 1 in. When I put 1 in here, 1/2 to the first, of course, is 1/2 times 5, that's 5/2. Put in 2, 1/2 squared is 1/4 times 5, that's 5/4. And it keeps going. So if I want to add up an infinite number of terms, this goes back to our first unit. If I want to add up an infinite number of terms, the only way that's possible is if my R value is between -1 and 1. That means it converges. If it does not go between -1 and 1, then it diverges and it shoots off to infinity. And then we have this formula when it does converge. So S equals U sub 1 over 1 minus R is the formula for when it converges. And I can do this because my R value is 1/2. And I can see it in my summation equation here, but I can also see from my first term to my second term, it's multiplying by 1/2, it's multiplying by 1/2, etc. So therefore S equals, my first term in this sequence, was 5. So that's 5 over 1 minus 1/2. So when I do that, it's 5 divided by 1/2. 5 divided by 1/2 is the same thing as 5 times 2 over 1. Good. So therefore, my infinite sum is 10.
Okay.
So on to calculus here. So we're going to start by talking about limits. We're going to kind of set the stage for a lot of the work we're going to do. And some of it's going to start with just like, here's a skill, this is how we practice it, this is what we're going to do. And then other times we're going to go, okay, so now we're going to apply it, and now you can actually see the real world piece of it. So sometimes it's going to be very skill driven, other times it's going to be very real world based. And we're going to flip back and forth between the both of them. Okay. So to begin with, we're just going to talk about some definitions and just make sure that you're as comfortable as you can be. So from the very beginning, we're going to talk about, so 5.1 is about limits and converging. We already talked about converging versus diverging. But so we're going to talk about a limit. A limit describes the output of a function as the input approaches a number. So the limit itself is going to try to figure out what is the output of my function as my input gets really, really close to something. And what you'll notice is I don't say your input is a number. We use the word approaches, keeping in mind sometimes it will be that number, but it doesn't have to be. So it's going to get, what happens when it gets really, really close to 2? What happens when it gets really, really close to 3? Okay, what happens when it shoots off to infinity? What we're going to be looking at, what I mean by as it approaches. So this is some of our limit statements that we're going to make. So the limit, L, so capital L they use for a limit. We're very rarely going to use capital L in our work. But the limit of a function exists as x approaches a real number a, if and only if the limit as x approaches a from the positive side, that's what this means right here. The limit as x approaches a from the positive side of our function equals L, and the limit as x approaches a from the negative side of our function equals that same L. The output has to be the same value for a limit to exist. So what has to happen is if I'm coming at, oh, here, let's just use this example. If I am looking at this value that was at -3, if I look at it from the right, if it was approaching a number, and as it approaches it from the left, if it approaches the same number, the limit exists. And we can figure out what that number is that it comes to. In this case, as I approach it from the right, my output, my y value is going up to infinity. And as I approach it from the left, my output is going down to -infinity. That's not the same value. Therefore, there is not a limit at 3, -3. But there could be at another value, like here at 1. There can be a limit right there. That limit exists because from the left-hand side, it approaches that value, and from the right-hand side, it approaches that same value. So we're going to look at figuring out whether or not limits exist graphically, algebraically, and analytically. Okay, so numerically. So what I'm going to have you guys do is, can you quickly sketch this graph? Put it in your calculator. And quickly sketch this equation. So As you guys are freaking out about what the graph of this looks like,
It's a line.
the shape is a line. It is a line. It looks kind of like this. I took out my grid marks just so that we didn't have any struggles. However, folks, it says x cannot equal 3. Why can x not equal 3?
Because if it was, then
Because
there's
there's
There is a denominator that would be 0, yes. And sometimes it's an asymptote, sometimes it's just a whole.
Can we simplify this? The equation?
Yes,
We can.
we can simplify it.
3, right?
Yep.
Great.
Okay, but there's some restrictions to that. So here is my graph. Folks, this is what we got. We just can't have a value at x equals 3. So when I look at this graph, if there was an asymptote here at 3, my graph would be shooting up to infinity. Is your graph shooting up to infinity to the right or left of 3?
Yes.
No.
negative.
No, it's not going to either of them. It's approaching that value. It's getting really, really close here. If you look at the table of your calculator, okay, if you look at the table of your calculator, it is going up by the same increments because it is linear with a, what's called removable discontinuity. There is a hole in the graph. We've seen this already. We've seen removable discontinuities before. So here's my graph. Now we're going to do the calc part of it. We're going to look at the limit as x approaches 3. We're going to look at the limit as x approaches 3. So when I look at my graph, here is 3. As x approaches 3 from the right-hand side, as x approaches 3 from the left-hand side, is it jumping around or does it look like it is a value? It looks like it's a value, right? We literally removed that point. It is a coordinate point. If I were to fill that point in here, I now do have a straight line with no issues. But because that denominator equals 0 at 3, I have to have a hole. I cannot have 3 in this graph. This graph is not continuous. Continuous means I can't draw a straight line to make the whole graph. I draw a straight line, I lift my pencil, and then I put it down infinitesimally close to that point where I just left off, and then I keep going. Okay.
You wouldn't call it discrete.
Nope, it is not discrete because it is, discrete would just be points, nothing connected.
Right. Okay.
Yeah. So now, with this graph, what I can figure out is what is the value at that spot. Look at your table in your calculator for a second. At 3, it says error. But if you follow the pattern in your table, what does it look like the limit equals?
6.
It equals 6. The answer equals 6. It doesn't approach 6. It is 6 since we're taking the limit as x approaches 3. The limit means we are getting closer and closer and closer to it, infinitesimally close to it on both sides. And when that happens, it is 6. So we are going to be evaluating these limits. So there's different ways we can evaluate limits. We can look at the graph. So we could see it in our graph. Okay, we could see what it got really close to. We can look at it numerically. We can plug a number in and see what we get. We can also do this algebraically, where we can rewrite. And I'm going to come back to that last example in just a minute, where we can do it algebraically so that you can see some of the different pieces with it. Okay.
But it's just then the value would be like whatever thought.
So that's where this first example is coming in. Okay, so we're looking here at the limit as x approaches 2 of x squared. So if I'm going to look at 2, I'm going to look at what happens really close to 2. But folks, sometimes I don't have to get really close to 2. I can just use 2. If I put 2 into my equation, does it give me an error? No. Put 2 in. What do you get?
4.
The answer to this is 4. The easiest way to analyze a limit is to substitute the value in. Because no kidding, if I have a parabola and I'm looking at what happens when I get really close to it, it's a point on the parabola. Poof, there it is. Okay. What makes it harder is if there's a hole or if there's a vertical asymptote and the value doesn't exist at that point. I can't have an x value of that. When I can have an x value, I just put it in. What happens when I get really close to 2 on both sides? It's just 4 because it equals 4 at that point when I plug it in. However, in B's example, when I substitute 0 in, can I substitute 0 in? No, so I cannot do this one numerically. I cannot just put 0 in and get what my limit is because it doesn't contain that point. There will be some kind of discontinuity on the graph when x equals 0, either a whole or a vertical asymptote. So therefore, from this case, I either need to graph it or do it algebraically. Let's do this one algebraically because you guys aren't going to get to always use your calculator. So to do this algebraically, a lot of times you just have to factor. Okay, so let's factor the numerator. So I'm going to write my limit statement again, the limit as x approaches 0. How can I factor my numerator? Factor out an x, good, and then you're left with 5 plus x over x. The work is crucial. You can't drop a limit statement. If you are evaluating a limit, you have to continue to bring that limit statement down. Okay, they will take off for not having accurate work. So then, do you see how these x's cancel out? That's a form of 1. So we can cancel those guys out. So it's the limit as x approaches 0 of 5 plus x. Now can I numerically substitute it in?
Yep.
Yes. So now we substitute it in and we get what our limit equals. So the limit as x approaches 0 of my function, 5 plus x, is what? 5.
What do we substitute in?
0
Okay.
in for x. Yep.
Or whatever number it's approaching.
Whatever it's approaching, correct. And then technically what it is, it's 5 plus 0, which equals 5. At this point, as soon as I substitute my 0 in, I can drop my limit statement because I'm evaluating my limit at that value. So as soon as I substitute a number in, you can now drop out that limit because now it equals a value. So for this one, when I have the limit as x approaches 5 of our function, if you try to substitute it in, can you do it? No. So for this problem, let's do this one graphically because there's no way I can factor this. So would you all please go ahead and graph this one? You don't need to use your calculator. It's transformation of the reciprocal function. Asymptote shifts 5 units to the right. Horizontal asymptote on the x-axis. It curves like this and like this. That's what the graph looks like.
You can't like graph it.
I know, you can estimate it because at x equals 5, does it approach the same number from the right and from the left? No, because from the right, it's going up to positive infinity. From the left, it's going down to negative infinity. Therefore, this limit does not exist. DNE. It was my favorite phrase in college to write. So for this one, this is a piecewise function. We can also find the limits of piecewise functions. So first things first, we're going to practice graphing a piecewise function, which is why I gave you a table. So please graph the top equation without your calculator. Graph the top equation for values that are smaller than 2, which means when I plug 2 in, what am I going to put on my graph?
3.
It's 3, but what's going to be at that spot?
Circle.
What kind of circle? An open circle, good. And then the bottom equation, you're going to put values in that are greater than or equal to 2. So making sure that you include 2, 3, etc. Again, do that without your calculator. So the limit as x approaches 1 of this function. So we're looking at what happens as x approaches 1. So this is at 1. What value does it equal as x approaches 1? 2, correct. It's the output. You literally found the coordinate point there. What if instead of saying as x approached 1, instead I said find the limit as x approaches 2 of my function? If we changed it to the limit as x approaches 2 of my function, so 2 is that piece where it was piecewise. Sometimes, even though it's piecewise, it's going to be one type of answer. Other times when it's piecewise, it will be this type of answer. So don't think piecewise functions are always the answer that is.
Is it?
No, the limit does not exist.
Does not exist.
A limit is not.
Because in order for a limit to exist, as you approach it from the right and as you approach it from the left, your output has to be the same. I don't care that the output of 2 is 8. If I'm looking at the limit, there cannot be this jump. It has to be the same as you approach it from the right and from the left. And we're going to be looking at more of these limits, and you're going to have some practice problems and stuff. So that's kind of like the first part, is just talking about limits and how they exist and all of that sort of thing. Okay, so onward to what happens instead of approaching the number. What happens if I'm looking at as x approaches infinity? Have we ever looked at as x approaches infinity before?
Yeah.
What did we call that? End behavior. We look at the end behavior of our graph. So when we start looking at what happens as x approaches infinity, or what happens as x approaches negative infinity, folks, we're looking at end behavior. And in all sincerity, if you guys were able to do this in Algebra 2, it's the same in calculus. When I look at my end behavior, so in this function, as x approaches infinity, what does y approach? 0. It's leveling out to the x-axis, so it's approaching 0. So we're going to be looking at what kind of asymptotes we have, specifically horizontal asymptotes, when we are looking at x approaching infinity and negative infinity. So a big piece with this is going to be end behavior. Okay, so we're going to evaluate these scenarios. So we're going to look at end behavior. So what happens when I put in a really big number, like 100? Okay, it's really not a big number, but if I put 100 in here, I get 2 times 100 plus 3, so 203, over 100 minus 4, which is 96. Well, that plus 3 really isn't a big deal. If I put in like a million, if I put $1 million in for x, I get $2,003. What's $3? So I pretty much have $2 million, okay? And then I'm dividing it by a million. If I divide $2 million by $1 million, what do I have? Oh gosh, you guys. Divide 2 million by 1 million and you get, oh, we know how to divide, not subtract. So when we're looking at end behavior, you're plugging in a really big number. And folks, you're going to do this without a calculator. So you need to be able to think about what's taking control. So let's try this again for B. 7 million over 2 million is 3.5. No millions. No millions. It's 7/2. Okay, and then the last one kind of looks a little different because I have the x squared first and then the x and then the constant, and then the denominator is vice versa. So you can go ahead and rearrange this if it helps you a little bit. It's up to you how you want to think about it. So go ahead and think about what happens if you plug 1 million in here. And if you absolutely need to use your calculator, go ahead and put this fraction into your calculator and see what happens when x gets really, really big. When you plug in 1 million and you square that million, what's 1 million squared? A really big number, a huge number. Minus 3 times 1 million, that's only 3 million. Think about it. 1 million squared, an incredibly large number. You just add those extra 6 zeros on. Now you take away 3 million, which really has such a small effect on that million squared. And then we're adding 2, whatever. So then in the bottom, I do 1 minus 1 million squared, which is pretty much just what? Negative 1 million squared, which equals what? 1 over negative 1, which is negative 1. Good. Good. So what we're going to be looking at is we're going to be looking at those horizontal asymptotes. Folks, that's what you're looking at. When you are approaching infinity or when you are approaching negative infinity, you're looking for your horizontal asymptotes. So I want you guys to take a moment and think through all of these. So A through I, and don't put them into your calculator. Just look at what happens with our end behavior. So because based on that end behavior, we have that horizontal asymptote. So when I put in a really big number on the top and a really big, that same big number on the bottom, where is my horizontal asymptote at? Y equals what? Not negative 1.
0.
Negative what? Negative 2. Because it's negative 2 million over a million, which is negative 2. So take a moment and find all of these horizontal asymptotes. Let's take like 2 minutes to do that, please. Okay, so here are all the answers. So let's look at B. Look at B. If I put a million in for X, the top is pretty much a million. And in the denominator, it's negative 3 times a million squared, which we've talked about is incredibly large. So if I have $1 million and I'm going to break that into a million squared, pretty much how much do I have left?
Nothing.
Pretty much 0. I always use the example of if I'm taking 1 and dividing by 100. If I have 1 piece of pie and I divide it by 100 people, how much pie does that person get? Pretty much nothing. Now instead, I'm going to take 1 pie and divide it into 1,000 pieces. How much pie do I have? Almost nothing. The more pieces I break it into, the closer my piece becomes 0, which is why my end behavior is y equals 0. However, here in C, if I have 1 million and I'm cubing it, that's incredibly large. And I'm dividing it by 1 million squared, which is still really big, but this incredibly large number divided by something big, is it going to converge to a number? No, it's going to shoot off to infinity as X gets bigger and bigger and bigger. That's why this one is none. So now what I need you guys to do is, I'm going to leave this up here. I'm going to leave this screen up here for you. Please flip your page to the next page, and you are going to fill in the table. I don't know if I fixed it on yours. Does your table, does it say f of x here still, or did I fix it? It's supposed to be p of x. So that's a mistake there. And then here, degree of, not g of x, that's q of x. So I want you guys to fill in this table based on the information here. So for instance, A is done. The degree of p of x is the top. So as we said here, p of x is the top equation, q of x is the bottom equation. So I want the degree of the numerator, so that's 1. Its leading coefficient is negative 2. The degree of the denominator is 1. Its leading coefficient is 1. And we had a horizontal asymptote at negative 2. So take a moment and fill in all of that information for these 9, please. So here is the filled in table. So hopefully I copied all the stuff in there right. Now I want you to analyze what you notice about the degree of P and the degree of Q and what happens with your horizontal asymptote. So look at the degree of P, look at the degree of Q, and figure out how can you use those to figure out where your horizontal asymptote is. So there is no horizontal asymptote when what happens between P, the degree of P of Q and the degree of Q. Let me say that again. There's no horizontal asymptote when I know what about the degree of P of X and what about the degree of Q of X. Yes?
When P of X is greater than Q of X.
When the degree of P of X is greater than the degree of Q of X. Correct. I have a horizontal asymptote at y equals 0 when the degree of
Q of X is greater than Q of X.
correct. And then I have these other situations. Y equals negative 2, y equals 1/4, y equals 2/3. So for those, what do you know about the degree of P of X and Q of X?
Very cool.
They are equal. So these are the 3 situations. When the numerator's degree is bigger, there's none. When the denominator's degree is bigger, it's 0. And when the degree is equal, then what do I know about my horizontal asymptote?
It's the leading coefficient of P of X over the leading coefficient of Q of X.
So it is the leading coefficient of your numerator, which our numerator was what, P of X again? Over the leading coefficient of Q of X. the coefficient. So when the degrees are the same, so such as here, okay, we divide them up. And then here it's 1/4. Here it's 2/3. So it's the ratio of the leading coefficients every single time. Now, here's the great thing, which is part of why we do this. If you forget this shortcut, you can always plug in a really big number and look at what happens at that value. But this happens every single time. This is our horizontal asymptote, which controls our limit as x approaches infinity, or as x approaches negative infinity. So that's why we're talking about horizontal asymptotes, because the horizontal asymptote will be what happens when our limit approaches either infinity or negative infinity. Therefore, pretty much, so here, let's just quickly do this. So what is the equation of the horizontal asymptote of this function? Y equals 0. Denominator's degree is bigger than the numerator's degree. What about the vertical asymptote? Correct. Vertical asymptote occurs where the denominator equals 0, provided it isn't a whole. It isn't a whole. And wholes always occur when they cancel out. Cancel out. So let's go back here. Right here, if I factor my numerator is x minus 3x plus 3. My denominator is x minus 3. If I were to graph this situation, as we did right here, there is a hole where? At +3, because those zeros cancel out. Okay. So that's where a hole always will occur versus a vertical asymptote. Okay, so based on what we just talked about, I want you guys to very quickly state the vertical asymptote and also the horizontal asymptote before we even graph this. So I want you to think through what would the vertical asymptote for this be and what would the horizontal one be. Let's start with the horizontal asymptote because we just came up with that. Horizontal asymptote, degree on the top and the bottom is the same, which means my horizontal asymptote is at y equals 2 because it's the ratio of the coefficients, 2/1. So I have my horizontal asymptote at 2. Where does my denominator equal 0? 1. Does x minus 1 cancel out with the top? Is there a factor of x minus 1 on the top? Nope. Therefore, there is a vertical asymptote at +1. And then you can plug in a number on each side and graph it. Because I know I have this horizontal asymptote, I can look at the limit as this function approaches infinity or negative infinity. So the limit as x approaches either positive or negative infinity of my function is what? Is 2, correct. Because it's my end behavior, it's where my asymptote is. So as x approaches infinity of this function, y approaches 2. As x approaches negative infinity, y approaches 2. From the right side, it's coming from the top down. From the left side, it's coming from the bottom up. We already know this equation. We've already used this equation. Infinite geometric sums. We talked about this. I kind of always talk about like what happens when r goes to, or when n goes to infinity. If I kept cutting like the piece of paper in half and then in half and in half and half and half and half and half again, as I keep going with that, 1/2 going to infinity is what? 0. Okay, because half of half of half of half is pretty much like I'm cutting nothing, which is where this formula, so if I put infinity in for n, again, I can't put infinity in for n. What happens as n approaches infinity? So what happens when n gets really, really big? Well, this value right here goes off to, not infinity, 0. Goes off to 0. So therefore, if that's the case, the limit as n approaches infinity of this function is just u sub 1 times 1 minus 0, which is 1, over 1 minus r. That's what the infinite sum is, equals, because we're looking at the limit as n approached infinity. We just talked about it like, hey, this is what it approaches, but it actually is that value. If I were to add up the infinite sum, it equals this value because we're taking a limit. Therefore, this is the geometric series formula. Okay, as long as the absolute value of r is less than 1, which means r is between -1 and 1, the series converges to this sum. If it's bigger than 1, the series diverges. Again, something we saw way early on. Okay, so wrap this up just real quick. So we looked a lot at what happens as we approach number. We looked at what happens as we go to infinity and negative infinity. We looked at horizontal asymptotes as well. So again, just trying to give you a basis that we are going to then build upon greatly as we keep going.